So I'd now like to go on to part 4 of this, which is to do with spin at the very small scale, quantum spins. So here's a rather classical, perhaps a rather naughty picture of an atom, which is the central positive nucleus and the electrons supposedly in orbits around it. We know that electrons are actually a smear of probability, but nevertheless, this is a sort of popular version of this. And it turns out that on the small scale, angular momentum comes quantized in units of h bar. Actually, h bar and a half h bar. So there are integer and half integer values of h bar. The half integer values are given to fermions, and the integer values are given to bosons. So the fundamental particles of nature divide up into those with half integer spin and those with integer spin. Well, the character of a spin depends on its magnitude. And here's a picture from A Brief History of Time, where we see a spin 0 particle. It doesn't do anything in particular when you rotate it. A spin 1 particle, you can rotate this and it will then point down. This spade will point down after you've been through half a rotation. To complete this, if you wanted to get it back to where it started, you have to rotate it by 360 degrees. And we're very familiar with that. That's the same with this object as well. A spin 2 particle, you only have to rotate it by 180 degrees, and it's back to where it started because the playing card is visible in the same way, whether it's up or it's down. So what about other particles? Well, the spin 1/2 particles are really the most interesting. They've got the smallest spin and they have the most pronounced quantum effects. The electron in particular is interesting. There are others like neutrinos, protons, and neutrons that have half spin, but the electron is interesting because the electron is really not like an object like this, which has its spin angular momentum because it's an extended object. An electron, in some sense, is a point-like particle, and the fact that it's got spin, you can't imagine it in these simple terms. It's a consequence of special relativity and quantum mechanics coming together. And this discovery was made by a Cambridge physicist, Paul Dirac, who managed to combine quantum mechanics and relativity. The remarkable thing about electrons is that they recover their original position not after a rotation of 360 degrees, but after a rotation of 720 degrees. And there is a famous demonstration due to Feynman, which I would like to try and do here, which demonstrates that. For this, I need an empty box. So Feynman's demonstration was this. You take a box, and it's got one end which is facing you, and you can tell which end that is because I'm holding it. It's got an up and a down, and if I take this box and rotate it, I can rotate it by 360 degrees, and it's back to where it started, roughly. But it's only roughly because my arm is not back where it started. But if I continue rotating my arm as well and the box, then after 720 degrees, we're back where we started. Now, that's an amazing thing, but that's just an analogy. And as we said before, quantum mechanics is a subject you really have to do for real. All of these sorts of analogies, they let you down after a while. So I think that just points to a very interesting study of the quantum mechanics of spin, which we haven't done in this course. With that demonstration of Feynman, let me summarize. Spin is a vector, and you use your right hand to take cross products, and right-hand rules very useful in describing it. There's a moment of inertia, which is angular mass. There's torque, which is angular force, and there's angular momentum corresponding to linear momentum. Conserved angular momentum, well, it's conserved, but some very interesting things can happen, and we saw the ice skater and the cat. And if you change angular momentum, that's when you have a torque or a force acting, then you have precession. And the wheel that we started with, which was floating so miraculously through space, was an example of a spin that was being precessed by an external torque. And then to end, we concluded with quantum spin of electrons, and we had this remarkable demonstration of Feynman's, which shows you that they are rather complicated objects in reality. So with that, I'll conclude. Thank you. Hold it very firmly, it's heavy, and turn around and face your colleagues. And you, right. Yeah, and turn around and face someone else. Do you see? Yeah, and give it to somebody else and let him. And turn around, face the young lady there, do you see? It wants to rotate.
Does it matter where you hold it?
If you hold it closer, it will be much more effect because you've got a smaller torque. Turn it, keep turning it up. Hold it at each end and then turn around and face these people.
Oh my God.
And keep going round. If you go right round.
It's weird.
Yeah. It's very strange, yes.
Yeah.
So one thing you can do is you can't pick this up with one hand when it's stationary, but you can pick it up with one hand if you're prepared to spin, because then you're going round. It's got a torque on it, and if I go really fast, it will rise up, do you see? But I'm going to get dizzy pretty shortly. Take it vertically and do your stuff.